Orbital Gardens, this is Mission Control. We are confirming acquisition of your signal. You are live in 5, 4, 3, 2...
Hello and welcome to episode 23 of Gardeners of the Galaxy, the podcast for all of the sentient beings in the universe who have a passion for plants. I am Emma the Space Gardener and I will be your host as we explore gardening on Earth and beyond. I've got a great guest on the show for you today. Morgan Irons made space exploration history last year when she sent the first Earth soils to the International Space Station. Morgan is a soil ecologist and she's going to be telling us about the importance of soil structure here on Earth and why she decided to send soil into space. That's coming up later in the show. In the meantime, we'll find out what's happening in the world of astrobotany, and I'll answer another listener question in the FAQ section. The next Spacex Resupply mission to the International Space Station is due to launch soon, on or after the 3rd of June. As part of its scientific payload, it's carrying some exciting plant experiments. Researchers from NASA's Kennedy Space Center are ready to launch their space chilies. This is Plant Habitat 04, an experiment that will grow in the advanced plant habitat. The APH has over 180 sensors and can regulate moisture levels, temperature, and carbon dioxide concentrations. This growing chamber is mostly autonomous and sends data from its sensors to scientists on the ground at Kennedy. The chosen chili variety is Espanola Improved. These New Mexico hatch green chilies are a medium heat variety that is happy to grow in controlled environments here on Earth. On the ISS, the experiment will run for around 4 months. During that time, astronauts should be able to conduct 2 pepper harvests. This longer duration experiment will be a more challenging test for the APH hardware than quick crops such as radishes and leafy greens. Chili peppers are an excellent source of vitamin C and other nutrients that can help supplement astronauts' pre-packaged diet. Peppers are also spicy, and part of the experiment will include astronauts giving feedback on the pepper's flavour and texture. We don't know yet whether growing in microgravity will have an effect on the pepper's spiciness. We all know that synthetic fibres contribute to global pollution and the particularly worrying issue of microplastics in the air, water and soil. And we know that natural fibres tend to be healthier for us. But the conventional farming of cotton also weighs heavy on the environment in terms of water, pesticide and fertiliser use. If you'd like to know more about the environmental costs of cotton, I'll put a link to a tree hugger article in the show notes for you. Cotton's high environmental footprint is why researchers from the Gilroy lab at UW-Madison are sending cotton to the ISS. Their TikTok experiment investigates how the structure of the cotton root system affects the plant's resilience, water use and carbon storage. They're hoping this research will help us develop more robust cotton varieties that use less water and fewer pesticides. Also on this flight are a couple of student-led plant experiments. Hutch Segan and Sophia Segan are hoping to explore how microgravity affects carrot seed germination. Their experiment will hydroponically germinate Naunt's half-long carrot seed on the ISS and compare results with a ground-controlled experiment on Earth. And Quentin Gage, Patrick Adamson, Noah Brightstein, Connor Morris and Grace Stumpf are flying an experiment to investigate the effect of microgravity on bean sprouts. The title of the investigation suggests they'll be using mung beans, however the blurb says adzuki beans, so that's not entirely clear. They aim to investigate whether bean sprouts could become a source of food for astronauts. In other news, Virgin Galactic's rocket plane has successfully flown to the edge of space. This is the one that's lifted aloft on a regular aeroplane before being released and igniting its rocket booster. Unity completed the first of 3 critical test flights, the aim of which is to have the spacecraft certified for commercial use by the end of the year. The next flight should carry 4 Virgin Galactic employees, and Sir Richard Branson himself should be on the 3rd. After that, Virgin Galactic has 600 paying customers waiting for a flight. That includes the Italian Air Force, which is paying for a mission to send several payload specialists into space with their microgravity experiments. Dr. Lynn Rothschild is an astrobiologist and synthetic biologist at NASA's Ames Research Center. She recently won a 2nd round of funding from the NASA Innovative Advanced Concepts program. The program funds early-stage research into technology that could one day be used for space exploration. Dr. Rothschild's research is into building habitats and other space infrastructure from fungal mycelia. That's the mushroom equivalent of a root system. The initial work focused on several different species of fungi. It explored what types of material they could grow on, including regolith simulants, and evaluated how processes like baking the mycelia change its structural properties. Their results included growing a stool that was perfectly safe to sit on, although it did take about 2 weeks. Now the team want to try more types of fungi, build more objects from mycelia, and expose their constructions to the conditions they would experience on the Moon or Mars. The temperature on the Moon's surface, for example, fluctuates dramatically over a lunar day, which is roughly equivalent to an Earth month. It may be possible to grow the mycelia during the cold nights and then use the hot day to bake them. The team is also designing inflatable scaffolds to mould the mycelia into different shapes and glues that could bind blocks together. I'm Emma the Space Gardener, and you're listening to Gardeners of the Galaxy. Now it's time for our FAQ section, and this time the question comes from Hazel Saunders, who asks, do plants grow upwards in zero gravity? That's a really great question, and it gets right to the heart of a lot of space research. What happens to things when gravity is taken away? Gravity is pretty much the only thing about our environment that hasn't changed over the course of Earth's history. Like us, plants have evolved to take gravity for granted. Here on Earth, plant roots grow down and shoots grow upwards. We always assumed that this behaviour was due to plants sensing gravity and knowing which way was up and which was down. We thought that when we took them into space, where there is no up or down, they would struggle to orient themselves. And to a certain extent that's true. Seeds that germinate in orbit send out roots and shoots in all directions. But only if you grow them in the dark. If there's light, then plant shoots grow towards it and roots grow away from it. These are examples of two different tropisms, biological responses that cause changes in plant growth according to environmental stimuli. When plants grow up and down due to gravity, that's gravitropism. If it's in response to light, then that's phototropism. And if you listen to episode 5, you'll hear space plant biologist Dr. John Kiss talk about his research projects into tropisms that affect the growth of seedlings in space. It looks as though, like us, plants can adapt to life without gravity. In fact, they may be better suited to life in space than we are. But while do plants grow upwards in zero gravity may seem like a simple question, we still have a lot to learn. So keep listening to Gardeners of the Galaxy, and we'll keep talking to astrobotanists as they learn more about how plants respond to gravity on Earth and how they adapt to its absence in space. Thanks to Hazel for asking such a fabulous question. If you've got a question you'd like to ask about space plants, then I'm here to help. You can find me on Twitter and Instagram at Orbital Gardens. Gardeners of the Galaxy has its own Facebook page, and you can email your questions to earth@spacebotany.uk. So now it's time to hear from our guest. Morgan Irons is working on her PhD in soil and crop sciences at Cornell University. Her research focuses on soil ecology and how interactions between the living and mineral components of soil contribute to soil structure. As part of that research, Morgan launched the first Earth soils into space together with biochar samples. Morgan is also the founder and chief scientific officer of Deep Space Ecology, a startup working to solve food security challenges in deep space and on Earth. Hi Morgan, thank you so much for joining us on Gardeners of the Galaxy. It's great to have you here.
Wonderful to be here, Emma. Thank you for having me.
Fabulous. So, you're here today to talk about some really exciting research because last year you made space exploration history by sending the first Earth soil samples into space, which I cannot believe it's taken this long. So that was your soil health in space experiment. Can you tell us about the experiment and what you hope to learn from it, please?
Yes, so this experiment was kind of a dream of mine that I've had for the last couple of years. I started looking at space agriculture back in the winter of 2014-2015 for us in the Northern Hemisphere. Pretty much out of that research, it became very apparent that there's not a lot of knowledge about the gravitational effects on soil microbiome, the microorganisms living in a natural soil environment, because we've never sent natural Earth soil up into space. There has definitely been microbiology experiments done in space. There have been growth medias used. Sand has been brought up into space. So there have been like mineral studies. There have been growth media experiments, but never a natural Earth soil. And we also sent biochar for the first time into space as well.
Yeah.
So I was very intrigued by what we could potentially learn about the gravitational effects on certain microbial processes in a natural soil environment. And so this experiment started coming together in, it was 2018, and we submitted to NASA CASIS back in 2018, and our first proposal was rejected. So it happens, and so yep, you just kind of have to roll with it and see what they said. And so did some rewriting, got some more key partnerships in the experiment, and then resubmitted. And the second time around, our proposal was accepted. And so one of the aims of this experiment is to identify the effect of the space environment on fungal and bacterial growth and activity relative to soil aggregate structure formation.
Okay.
So I said a lot in that sentence.
You did.
So soil aggregates are pretty much those clumps of soil. If you dig your hands down into a nice fertile soil, you should have clumps come out, and those clumps are soil aggregates. And those soil aggregates are stabilized or held together due to chemical interactions, but also fungi and bacteria also play a part in helping to bind together those minerals as well as the organic matter and organic carbon that's in that soil. And soil aggregates are very important for soil health because they are a soil health indicator. They help with biogeochemical cycling, so water cycling, carbon cycling, nitrogen cycling, all of that, as well as helps with the structure of the soil. You need those aggregates in place to create the macro and micro pores of the soil, which helps with, of course, water and air exchange in the soil, as well as helps with plants being able to bring their root systems down into the soil to reach different nutrient sites and water sources, as well as to interact with the other plants around them and the microorganisms in the rhizosphere. So soil aggregates are extremely important. And my PhD research currently being done at Cornell University is very much interested in this microbial aggregate interaction and how that affects carbon cycling in the soil. And so I wanted to take my research into space since I've been doing space agriculture research for the past couple of years. And so this experiment was that opportunity for me to see if we take natural Earth soil, if we take biochar out of Earth gravity and put it in a microgravity environment, keeping everything else as constant as we can, will we see any changes in that underlying mechanism of how the microorganisms interact with soil minerals, soil organic matter? And we see that through how aggregates potentially form, or if they form at all, as well as the decomposition and carbon cycling that we're seeing as well. And so out of this experiment, we are definitely doing some interesting analysis with the samples that we've gotten back, which we got back this last January.
Excellent. That sounds really exciting. I'm really looking forward to seeing what comes out of that. So as you say, now the soil samples are back on Earth. What kind of changes are you looking for?
So we have several analyses that we are running on these samples. We have a partnership with Dr. Matthias Rehlig over in Berlin, Germany at Free University of Berlin. So he specializes in the soil microbiome and doing that kind of work. Okay. And so we sent some subsamples of our samples over to him. He also provided the Berlin, Germany soil that we use. So we sent up a soil from Ithaca, New York, a soil from Berlin, Germany, and then the biochar media that we received from Bio365, which is a company here in Ithaca, New York, that creates biochar to help with greenhouse production, farming production. And so what he is doing, he's currently running the microbial analysis. So understanding how the fungi species may have changed in microgravity as well as the bacterial species. We're also looking to see if any pathogens have potentially
snuck in,
evolved or snuck in. Yes, because that's definitely something that NASA and other space industries are interested in. They're very much hesitant when it comes to bringing any microbial abounding substance or substrate into space because of the potential evolution that can happen into a virulent strain and things like that. So there is a little bit of convincing that we had to do in this case, which of course did put some restrictions on what we could do with this first experiment. But I'm hoping that with the information that we gained from this experiment, it could help make it a little bit easier
in future.
Fingers crossed, to do another ISS experiment to further the knowledge that we're gaining from this one. So yes, he is running the analyses on those subsamples to see what the microbiome was doing up in a microgravity environment. Over here, we are running analyses on the carbon cycling. So we are looking at the decomposition. So we had wood carbon in the soil, toothpick, wood carbon, in the soil. And so we're looking to see if decomposition has occurred, as well as analyzing the carbon within the toothpicks before and after. We are also looking at the aggregate stability as well as the size fractionation of the aggregates. And what does this mean? So before we sent the samples up into space, I sieved the soils, the mineral soils, which is the Ithaca soil and the Berlin soil. I sieved those down to a particular aggregate size. And pretty much why we do that is to see if there are any macro aggregates that form above that size. Or if they all stay below that size. And so that can give us a really good indication of whether aggregation was happening or if it was more like the aggregates stayed about the same or they were actually disaggregating, if that's a word. Sometimes it's just like, that's the best way to describe it. The aggregates are falling apart. So we do size fractionation, which is pretty much this method of using different sized sieves to separate the different sizes of aggregates, because you have the macro aggregates, which are the bigger aggregates, and then the micro aggregates, which are the smaller aggregates. And we kind of see the span of how many micro aggregates we have to macro aggregates. And this can inform us, like I said, on what's happening in the soil and how the microbiome may be interacting with the soil's structure. So we're doing that. We are also looking to see if we can do a little bit extra. Some of my skill set is that I have experience using electron microscopy. And so we're looking to see if I can actually put some of the soil aggregates into a resin encasement and then analyze them using scanning electron microscopy or transmission electron microscopy to see if we can really look at a cross-section of an aggregate and see how the pore structure may be different or where microorganisms are sitting within that pore structure, which would be very fascinating to see if anything's changed in that regard, especially since these soil samples have been frozen in pretty much negative 80 degrees Celsius conditions since they left space. Because we wanted to keep things as stable and representative of what happened in space as possible. We're working on those analyses right now and starting to get some information back, but of course we're still in the process, so I can't really say.
Still early days,
still early days, but I would definitely like to do another ISS experiment
Yeah.
to bring further data to what we're going to potentially be finding from this experiment, to see if what we're seeing is some kind of statistically significant association with the absence of gravity in the system or not. This was definitely a learning experience, which for for a lot of space experiments, it's a learning experience.
Yeah.
And so there are definitely things that I would have done differently now that I have that knowledge, as well as things that I would potentially keep the same. And we're definitely getting interesting data from this ISS experiment, and it will definitely feed into the next experiment that we hopefully do.
Okay, so you're talking about, the importance of living soil, and Earth so far is the only planet we know of that has such a living soil. So what do you think of the prospects of us farming on the moon or in a Martian regolith? Does your work move us towards that in any way?
Yeah, so that's always on the back of my mind, you could say. It's where I started my research. So, like I said, I started this research back in the December-January time period of 2014-2015 when I was an undergraduate at Duke University. And I was very much fascinated by this connection between, like, closed ecological systems and space habitation, because I had been trying to figure out a way to connect my passions for the environment with space. And really at that time, a lot of the focus was still on kind of just rockets, rovers, the highly robotic, highly engineered elements of space. I had never really heard or seen anything about growing plants in space, even though it was happening at that time. I just wasn't exposed to it. And it wasn't really out in the media at that time. I believe like the Martian movie really brought it out into the general public a bit more.
Yeah.
And that was happening right in the middle of my research. And so I would always get you're the botanist, right? I'm like, I'm not training to be a botanist, but space agriculture, yes. So what I've learned from starting that research at Duke University and then moving on into a PhD where I'm working in soil and crop sciences is just how important the soil is to any agricultural ecosystem. 95% of our food comes from the soil. And so we rely so heavily on the soil here on Earth for our food production. And when we're thinking about going out into space and potentially having long duration missions that would be more sustainable if they are Earth independent instead of relying on a potentially politically charged, financially charged supply chain, you have to really start to think about what elements of your system will lead to that sustainability, will lead to that Earth independence. And agriculture, of course, is one of the major parts of that. How will you be feeding the crew members that are there on site potentially for a couple of months to a couple of years? And so I started this research and was very fascinated with how we can apply environmental science, soil science, ecology into this conversation that has been really dominated by engineers for a long time. Yes, there have definitely been biologists involved in everything, but a lot of research has been very closed off from other disciplines. And it really wasn't until the turn of the century that we've started to see this idea of multidisciplinary, interdisciplinary work start to come forward, where you break down those walls and actually start talking with people in other fields and actually do collaborations to figure out like how we can solve a problem using a different perspective, using a different field of study. And so that's one thing that I really wanted to bring forward into the space industry, is this need for multidisciplinary work. And space agriculture is one of these elements. It really needs a multidisciplinary lens. And so the engineering is very important, but also your source of your food and your connection with the environment, because we see that not only do we get our physical needs met, by the natural environment, but we also receive mental, psychological, emotional benefit from the environment as well. Just being able to step outside and feel the wind on your skin and just see greenery around you can have such an impact. And so ultimately what I'm trying to say is that it's very important that we do more research on how we can best use the lunar regolith, the Martian regolith, to create more large-scale field-based systems. And of course, there are some barriers in the way of that. Of course, we have perchlorates in the Martian regolith that are of high concern because they are harmful to human health. So we have to figure out how to best mitigate those perchlorates in the Martian regolith. And there's definitely research going on here on Earth. We do have perchlorate contamination here on Earth because it is a byproduct of explosives, rocket fuel. So it's commonly found around military bases, industry. And so you can actually go and look at papers that have been written on this about how to do environmental mitigation with contamination of soil and waterways with perchlorates. The experiment that I ran when I was an undergraduate used a Mars regolith simulant. I realized how difficult it is to grow in Martian regolith just through that simulant. I can only imagine how difficult it will be in a space environment. Through that experiment, I had to start developing different methods that will be important for when we use Martian regolith for agriculture, for example. And this connects back kind of to what I'm doing now. Martian regolith is very much like cement when water is added to it. You add water to it and it just kind of becomes this cement crust layer. And it has a lot of sand and dust in it. And so it doesn't really have great aggregate structure in it either. And so one of the things that I learned when I was going through this Mars agriculture experiment was when I would add the water to the regolith, I would allow it to sun dry and it would create that crust. And then I would take a spade and really work at it and break it up, but not break it up into really small pieces. I would allow those big pieces to still be present. And then I would add more water to it. And I did that a couple of times. And pretty much what I was doing was I figured out that for the water exchange and air exchange to happen in this environment, I needed to create the aggregate structure. And using water as kind of that initial step to start forming bonds between minerals in the soil was important. And that's what I was seeing. And then I brought in the ideas that surround this theory of ecological succession. So how do ecosystems form over time? Because some of the ecosystems that we may have outside may have started as bare rock. For how many millennia ago that may be, and have formed over time. And so how do we form an ecosystem from scratch, which is pretty much what you would be doing on Mars. And so forming that aggregate structure, starting to introduce microorganisms and pioneer species that can live in that more rough environment is very important. So I really learned the importance of those initial steps. So I think it is possible to develop an agricultural system on another planet. We just need to make sure that we are approaching it in a sustainable way, making sure that we do not repeat the same mistakes that we've made here on Earth.
Okay. So you've had your experiment back from space and you say you'd like to do another one. And actually, on your LinkedIn bio, you do say that you're the recipient of an experimental payload on a Blue Origin New Shepard launch this year. So can you tell us a bit more about that?
So back in 2019, I wrote up a research proposal for the Ken Souza Memorial Space Flight Award. Ken Souza having been a space biologist who made such a large impact in the space industry with his work and just his mentorship as well. I wrote up this initial experimental design and was awarded the Ken Susan Memorial Spaceflight Award. And with this award came the opportunity to actually have my experiment be on a Blue Origin New Shepard launch. The launches that they're doing are parabolic flights. Yeah. So pretty much it launches, it gets into microgravity for a few minutes, and then it comes back down. Fingers crossed, we have this experiment happening potentially this fall, maybe in the spring of next year. With this experiment back in 2019, I was looking to pair it with my ISS experiment, kind of have it be complementary to that experiment. So very similar, sending up natural soil samples, biochar samples to see what would happen in that parabolic environment, as well as see like the rocket effects.
All the vibrations,
on
yeah.
The soil. Yep. To see if there could potentially be a better way to send up soil samples. So in this case, there could be some fundamental knowledge that comes out of it, but also methodology development as well from this experiment. Graduate work is kind of like being part of a startup. You're just kind of always in fluctuation with like what direction you're going in. And
yeah, so your company is Deep Space Ecology, Inc. Did you want to talk a little bit about that?
Yeah, definitely. So Deep Space Ecology is the company that I co-founded with Lee Irons, who is my father, back in 2016. And pretty much Deep Space Ecology was created based on the research I was performing at that time at Duke. And it also came out of going to my first actual space conference, where we went and nobody was talking about space agriculture. Mm-hmm. It was mostly focused on rockets, landers, very engineer heavy subjects. And if space agriculture was mentioned, it was like, oh, yeah, that's we're good on that. And I'm just like, no, it is so much more complicated than this, y'all. So out of this conference, we saw this open niche that no one was really publicly filling at that time. And so we created Deep Space Ecology. It started off really to get the word out about the need to have multidisciplinary work in the space of space agriculture and to invite different voices, especially the environmental science, biology, soil science voices into this conversation. And my research was starting to show why we needed that. Because I was figuring out things and finding out things that we could potentially do in these systems to solve challenges that have happened in past systems. So bioregenerative solutions, you could say. Deep Space Ecology has very much evolved. It's been a interesting learning curve experience, having a company and figuring out where we can take it. But I think what we've ultimately become is where we very much are an integrator of systems. We've come to realize that there are solutions being developed in the agricultural industry, especially with this movement in digital agriculture, that could be spun into space, that could help solve some of the challenges that we're currently facing in the space industry when it comes to space agriculture. And so Deep Space Ecology is kind of this connecting point right now for bringing the space industry and the agricultural industry together, and how we can integrate systems together to help solve food security challenges and sustainability problems here on Earth, as well as in the deep spaces of the moon, Mars, and beyond. We have developed a new system called Evercroft. Okay. You can go onto Deep Space Ecology website and look at Evercroft, and it's pretty much the Earth market for us. How we are helping farmers as well as people who work with food here on Earth, helping them with their supply chain challenges here on Earth. But yes, we are pretty much developing our Earth market, and our Earth market will also help us with our space market as we move forward with that.
That sounds amazing.
Yes.
And to be doing that while you're doing a PhD, you, you must be so busy.
I'm definitely very, very busy.
Okay, so finally, if we move on to a little bit less of a serious topic.
Yes.
So if you had the opportunity to join a settlement on the moon or on Mars, with your regolith soil structure already present, if you could only take one plant with you, what would you choose and why?
Ooh. Yep. I always love this question. I was really thinking about it, and I think I would take the Rumex acetosa.
Sorrel.
Yeah, sorrel. Yes, exactly. And the reason why I would do sorrel in particular is because it's a multifunctional plant species.
Yeah.
So sorrel, in particular, this acetosa species, has a very lemony flavor to it. So it creates this burst of flavor that would be great for, of course, food. And this is something that the food team down at NASA Kennedy Space Center is interested in. These bursts of flavors that allow you to kind of have an interesting menu item. So I was very much attracted by that about sorrel, and I love eating sorrel myself. It also has a lot of health benefits as well. It is loaded with vitamin A and C, so that's, of course, great for your immune system.
Yeah.
And it also has a high potassium content as well, which can help with blood pressure and blood circulation. And sorrel, traditionally, as well as in indigenous communities, has been used for medicinal purposes as well. There was also an environmental element that I found very interesting with it. Certain soils have a high content of aluminum.
Okay.
And sorrel can actually be used in these sites to take up the aluminum and actually bind it into non-toxic forms.
Okay.
Sorrel is also has a lot of genetic plasticity, meaning that it can pretty much survive in a bunch of different conditions, which is why sorrel is found in grasslands, in disturbed sites, is able to adapt really very nicely into these sites. And so that's another reason why I was interested in it, because when we're looking at space agriculture, pretty much the Martian environment is this very extreme, harsh environment, and sorrel could potentially be one of those pioneer species that can come into that environment and help with remediation and be able to survive in that kind of environment. So I just found that super fascinating. And so ultimately, I think that would be the plants that I would like to bring with me into space.
It does sound like it might make a perfect space plant. Yeah.
Yeah.
Yeah. No, that's really great. I love sorrel. I've got some growing in the garden. It's fabulous. And it is pretty tough. So it's not phased by my gardening efforts. So it's good. Thank you so much for coming on the show. It's been fabulous talking to you. There's some fascinating research that we're going to be keeping an eye on.
Yes, I am very excited to see what comes out of this. And thank you so much, Emma, for having me on your podcast.
It's been an absolute pleasure. Thank you. If you read my blog, you'll know that over the last year or so, Ryan and I have been exploring what we would eat on Mars. On the ISS, astronauts have a reasonably large range of menu items to choose from. However, they inevitably eat the same things regularly, leading to menu fatigue and a lack of appetite. One way to overcome this on a long-duration mission, such as a trip to Mars, would be to give astronauts the ability to cook their own meals from a selection of long-life and shelf-stable ingredients. So Ryan and I have been trying that out, culminating in us spending last Christmas on Mars. Moving forward, I'm going to be documenting our continuing experiments in a free email newsletter. If you'd like to join us on that journey, then you can sign up at tinyletter.com/meals on Mars, and I'll put that link in the show notes for you. And on the 27th of July, Gardeners of the Galaxy will be a year old. I'm thinking of doing something special for the birthday episode, so do let me know if you have any ideas. That's it for this show. You'll find the show notes on my website, theunconventionalgardener.com, which is also home to a virtual tip jar for those of you who would like to support the show. If you want to become a regular supporter, you can sign up via patreon.com/Gardeners of the Galaxy to access extended episodes and bonus content. I'd love to hear your comments on the show. You can comment on the Podbean homepage, on my website, on Twitter, Facebook or Instagram, or you can email me, and the address for that is earth@spacebotany.uk. I'll be back in a couple of weeks with episode 24. Thanks for listening. Goodbye.
Orbital Gardens is mission control, confirming termination of signal. We've had a message from Mark Watney. Next time someone's near the rover, can they please check under the seat? He thinks he's left his house keys there. Mission control out.